class of the year. No, I'm just kidding. After today, 2 more lectures.
What?
And we are a handful of reactions and just a couple of mechanisms away from being done with everything as well. So we are in the home stretch for sure. On this worksheet that has alpha hydrogens on the front, we've got a few reactions left to explore on the back. We wrapped up with the chloroform reaction last week.
All those?
So right now we're filling in we are using this roadmap.
Can I get a handout? I forgot mine at home.
Oh, it's such a defeated request.
So like, shoot.
All right, so what do we have here? You have all of the skills. Do you have a question from the homework?
It was on the lecture for same stuff.
You have all the skills to name this compound. In fact, you have all the skills to name most of the compounds on this worksheet. I think malonic ester would be the hardest one to name if you didn't have anything else. All the other ones are, no, the cyclic esters either. I would not expect you to name the cyclic esters. We didn't go through naming those.
It's on the test.
Cyclic esters
Naming.
on the final exam? Did you see it in your unit tests?
Not in the unit test.
Yeah, you did. Unit 4 unit test, you saw nomenclature. Unit 2 Unit 2 test, you saw nomenclature. Unit 1, you saw nomenclature. Unit 1 was OCHEM 1 nomenclature. Unit 2 was benzene. Unit 4 was aldehydes, ketones, carboxylic acids, and esters nomenclature. So yeah. You definitely could see nomenclature like this on the final exam. So what's its name? This is a compound I want you to recognize, but it's also one I want you to realize you have the skills to name outside of its common name using a systematic name.
Is it ether the higher priority than the?
No ether here. Ester.
Oh yes.
Yep.
Maybe something like ethyl diacetoester.
So this is an ethyl group, which means it will go at the front, yes. But then you call it a diaceto, which is on the right track, right? You're remembering part of the name, but it's not a diaceto. Oxo would be a good way systematically to name this as a substituent, but we wouldn't call it dioxo because this is not an oxo group. Ketones and aldehydes can be oxos as substituents to higher priority groups. Esters won't be an oxo. Russell, did you raise your hand?
Yeah, I was going to say if it had oxo in it.
It can have oxo in it. So that is taking 2 suffix stoppers, and we're only allowed 1 suffix stopper. So it can't be 3-one butanoate, because one is a suffix stopper. 08 is a suffix stopper. That is when we would use oxo. So Brett, your same locants, but now using the correct substituent name. Good. Ethyl, 3-oxo, butanoate. Is that systematic or is that common? Very systematic. I also want you to know its common name. I want you to at least recognize its common name so that it seems familiar to you. Yes, Now with the alkyl group in front, ethyl acetoacetate. And this is where, Jacob, I think that was you that said, is it a diaceto group? No, it is an acetate substituted by an acetate, right? Or an acetate with an aceto substituent. I hate it. But that's the line of thought that they were on. It's like there are two carbon-carbonyl groups connected together. Lovely. All right. The reactions that we're looking at here will include alkylation, specifically alpha-alkylation. On the right-hand side, we'll show one equivalence of alpha-alkylation. On the left-hand side, we're going to show two equivalences of alpha-alkylation. What are we trying to imply? What change will happen during an alkylation reaction? Add a carbon group. Perfect. You know, we could also have called acyl addition with Grignard's alkylation because you're adding a carbon group. But you're doing it in a more complex way. You're removing a pi bond when you use a Grignard. Here, we're doing alkylation, and we'll be doing it by substitution at that alpha position. We learned about alkylation of alkynes back in OChem 1. You can deprotonate a terminal alkyne, and you can take that alkyne to be a nucleophile, and then you can run substitution using that alkyne as a nucleophile and alkylate the nucleophile. That means, once again, we're going to need to get nucleophiles out of our alpha positions. Luckily, we can get nucleophiles out of our alpha positions because we can deprotonate those alpha positions. They're fairly acidic. They're even more acidic than this terminal alkyne. But we'll need typically a series of steps if we want to do it twice. We'll need a base and we'll need an electrophile. We'll need a base to deprotonate. We'll need an electrophile that can be substituted by the new nucleophile. And you'll often see this done in separate steps so that the base itself doesn't act as the nucleophile on the electrophile. So first, a base. What would be the base that I want here to deprotonate the alpha position? Options are hydroxide, methoxide, ethoxide, aldehyde. Sorry? Hydroxide will saponify the ester. If we add hydroxide, we will get a carboxylate and an alcohol. Shoot. So, we don't want to use hydroxide. Ethoxide is a great choice. We could also use aldehyde. Absolutely. Do I need to call you when he's ready to be picked up? Yeah. Okay. Welcome. So we'll use ethoxide because it is the base that matches our ester linkage. I'm going to write it as ETO minus. I want you guys to realize that's the same as saying NaOET, where I just ignore the spectator cation. And if you like to keep your carbon chains, then you can draw ethoxide as a carbon chain. What's the difference between all of those? Personal preference. After we've added the base and we have deprotonated our alpha carbon, we can add an electrophile. This should be typically a primary alpha carbon, a primary alkyl halide. So let's show something simple like methyl bromide. Not actually a primary carbon, that's a methyl carbon. It's not attached to any other carbon. But what I'm saying is low degree of substitution. Our carbon chain stays the same, but the alpha position is now alkylated. And again, we can do that twice if we have more than one position. We can do that twice if we have more than one alpha hydrogen that can be removed and turned into a nucleophile.
Why'd you do the first step?
First step deprotonates, so it gives me my nucleophile.
And you use that one just in case it does the side reaction?
Correct. If it does any sort of chemistry with the ester, I want to make sure it doesn't change the nature of the ester.
It turns into the product.
It
A reactant.
yeah, if this base reacts here, it doesn't change anything. Yeah, it doesn't actually transesterify it. And of course, we learned that you could actually draw this structure like this. Woohoo! Right? That's the resonance hybrid form. All three of those positions are sharing the negative charge. Both oxygens and the alpha carbon. But let me clarify, or let me ask if you can clarify why this alpha position is deprotonated and not this alpha position. Secondary would increase the acidity. It would decrease the pKa, but that's not the major factor. That would change its pKa by like an order of magnitude because of increased resonance. This alpha position is alpha to 2 carbonyls, has a lot more resonance in the intermediate than this alpha position, alpha to only 1 carbonyl.
It's got to be a ratio, right? Or is it pretty?
Yes, it is a ratio. Here's the ratio. This has a pKa around 11, and this has a pKa around 20. So the difference there is 10 to the 9. That's the ratio.
It's a pKa thing? I thought it was a resin.
It's a ratio of the pKa's. This gets deprotonated 10 to the 9 times more often than this gets deprotonated. That's the difference in the pKa's, which tells us a difference in how often they form. So for every one of these that gets deprotonated, a billion of these other alpha carbons get deprotonated. This is actually something that limits your percent yield and limits your purity in a real sense. When you go into the lab and you remove impurities, you remove side reactions, you're removing that 1 in a billion chance that this position does the reaction instead. It happens. So what we're showing are major predicted products. This is also why if you worked in an organic research lab, you probably will never report 100% yield. If you do report 100% yield in an organic synthesis lab, people will think you did something wrong, or they will question the purity of your product. You never have complete conversion. Certainly not to the molecular level. All right. Look at how this product here still has an alpha position that is double in resonance. That means that this is still able to be alkylated. So that's what we'll show here is how we can do a second alkylation. I also want you to recognize that in this position, the acidity changes. Can you tell me how the acidity changes from our starting material to this product? More acidic because? Same amount of resonance?
substituted group?
More substituted carbon. Which doesn't actually mean the more substituted carbon makes it more acidic. It's the more substituted alkene resonance form that makes it more acidic, right? When that alkene forms here, it's more substituted, more stable. All right, so first, NaOET. Second, let's do the same thing. CH3, I'm going to change the nature of it a little bit. CH3I. Essentially the same electrophile because it's providing me a methyl group. Could I have put CH3OH? Yeah, the OH now has an acidic hydrogen, and OH is not a good leaving group. So halogens are the way to go. Then I'll deprotonate a second time. After I form this product, I'll deprotonate it again to make a new enolate, and then I can add a different electrophile. I mean, if I wanted to, I could add the same thing, but then I could just do steps 1 and 2 a little bit different. Here, I'll just add a new electrophile. Let's add benzyl chloride. pH, CH2, Cl. If you're not a fan of seeing it in that condensed form, here's its bond line structure. That di-alpha-alkylated product can be a little tricky to draw, especially when the groups get more and more confusing. Is it chiral? Sure, absolutely. So which chirality forms? Both. The intermediate, which would actually be this, is achiral. All of that central carbon is sp2. It's in resonance, which means it is asymmetric. Sorry, it is symmetric. It is achiral. And after that carbon attacks the electrophile, it becomes chiral again. Here's a good way to make sure that you add all of the carbons in this synthetic step. Count through your nucleophilic attack and make sure that everything is bonded the way it should. So let's say I start counting from the left-hand side and my nucleophile is position 3. Three attacks carbon 4. So when I draw my product, I've got 1, 2, 3. 3 is bonded to 4. But 3 also attacks the benzyl carbon. So I'm going to call that, you can call this whatever you like, I'm going to call that 4', because it's also attached to 3, so it makes sense that it is also carbon 4, but I want to make sure that I distinguish it from the other carbon I labeled as 4. 4', and then that would make the benzene ring at 5'. So here's 1, 2, 3. 3 attacks 4'. 4' is attached to 5'. Great. I've added all of my carbons. I haven't lost track of anything. Here is one of the useful features of acetoacetate and malonic esters in doing alkylations. We can run a new type of reaction after alkylating. These acetoacetate and malonic ester, these are the best reagents for doing this alpha-alkylation. Doesn't mean they're the only ones. They're just the best. Can you reason why they would be better than our aldehyde alpha carbons, ketone alpha carbons, or ester alpha carbons at doing alkylations?
Resonance, and there's only one side. There's only one way to go on this one. And
So kind of like you've got targeted regiochemistry.
Yeah.
And their pKa is much lower, so it's a lot easier to create them as nucleophiles. So this would be like over aldehydes, ketones, and esters. These are the ones that we'll use for alpha-alkylation. There's another reason that synthetic chemists would like to start with these as starting materials, and it's because of a new reaction that they can do afterwards that again changes the carbon chain. And that is this reaction, decarboxylation. Has anyone ever decarboxylated anything? You want to share? That's okay. You can plead the fifth. Anybody else ever decarboxylated? What might it mean? Removing. Okay, what are we removing? A carboxylate, like the anion, the conjugate base of a carboxylic acid.
That is what that word sounds like to me.
Okay, I hear it. Decarboxylated. So maybe we need basic conditions so that carboxylic acid becomes a carboxylate, and then somehow we can get rid of the carboxylate. Anybody else have a idea of what decarboxylation could mean?
Isn't this where you bake your weed? Am I thinking of this?
You can do that. When you bake weed, it decarboxylates.
Okay.
Yep. That is a very applicable.
With just the heat, you don't do any. Okay.
You don't have to add anything else. Exactly. The carboxylic acid in that case, which means it's not in basic conditions, reacts under heat and leaves. What would we form as a byproduct of decarboxylation? CO2. CO2 is a very stable molecule. It's very common. The carboxylic acid contains a CO2 group, but it also contains an H. So where does the H go?
just burn the product or whatever touches the product.
The H?
Yeah, just acidic now.
So now the environment is just having protons floating around? Potentially.
Would it also leave with water?
Ooh, so thinking that maybe there's another OH somewhere else in the molecule then that could pick up the carboxylic acid's H to create CO2 and water. These are good ideas. Let's draw the structures so that we can see it. Decarboxylation from this starting material is a two-step process because we don't have a carboxylic acid. Would you agree? We have an ester. How can I make a carboxylic acid from this ester? So my question is, to show you decarboxylation, I need to make a carboxylic acid. P2O5 will take two carboxylic acids and make an acid anhydride. So does not start with an ester. Chromic acid, CrO3 with H2SO4, will not do anything here. Not a bad guess. How do I make a carboxylic acid from an ester? I hope you're thinking of that diagram that is god-awful, right? And it has all of the acid derivatives and how they relate to carboxylic acid. That would be the roadmap to go find. ROH and H plus react with carboxylic acids to make esters. I want to start with an ester. So you're in the right spot.
OH and H3O+.
Good. Oh, not OH. Not OH and H3O+. Those wouldn't exist together.
Oh, I have like a one.
First,
First hydroxide.
yep, and then H3O+. And also H2O and H3O+. So we have two routes. We could saponify hydroxide, reacts with the ester, and then acidify. Or we could just put H2O, H3O+, acid catalyzed hydrolysis. When you guys were doing esterification in your lab projects, it was the equilibrium between these two reactions that we wanted to try and overcome and get a good yield. We could have also put first OH minus, second H3O+. Would have done the exact same thing. Now that I have a carboxylic acid, I can decarboxylate. Just like Michaela said, I don't know why I called you that. I have your exam, I think that. All we need here is heat. Delta here is just representing heat. There is no other reagent needed for decarboxylation. This is just hydrolysis, which is what we need in order to set up for decarboxylation. If I cleave off a carboxylic acid, or sorry, a CO2, that means that I'll lose this carbon, but not the alpha carbon. If the alpha carbon loses the bond to the carboxylic acid carbon, it would go from CH2 to CH2 plus, minus. Why would it want to sit without a full octet? And again, we were wondering, where does this hydrogen go? This alpha carbon can take that hydrogen and terminate as a CH3 group in this case, or a CH group in a dialpha alkylated, or a CH2. So this gives us, in this case, a ketone and carboxylic acid. Sorry, thank you. Carbon dioxide. Ketone and carbon dioxide. We do not have to write the hydrolysis and the heat separately. If we run hydrolysis at boiling temperatures, then we can also see this, this process happen at once. There is an important caveat. Not every molecule that has a carboxylic acid goes through decarboxylation. This requires a beta-acyl acid. I almost wrote beta-keto acid because that's the way that it's often said, but it doesn't need to be a ketone group. It just needs to be a carbonyl. But if it's not related at a beta position, then it will not work. So first, let's take these other products that we made and let's look at their decarboxylation products. H2O, H3O+, and heat with our methyl alphylated, and then H2O, H3O+, and heat with our methyl and benzyl substituted product. Recognize that we're not showing hydrolysis and decarboxylation as two separate steps. We're just writing them at once. We don't have to say one, then two. You can do this simultaneously. And you guys know I'm a stickler for the one and the two, because that tells you logistics about how you run this. Feasibility. if you're struggling in predicting the product, find a way to use this example from before as a reference. Count your carbons. Is this the product? Or you're just, no, you're just copying it.
Yeah, he's copied this one.
This one's good. Yeah. It's a bit of a funky way to draw it.
Yeah, it's how my brain likes to draw.
So now that you have that, maybe draw it as like, oh, this is what it would be as a normal molecule. Yeah, just like, yeah. Yes, exactly. Yeah. Good on the top, good on the bottom. Yep. All right, if you think you got it, turn to neighbors that are also done and see if they got it.
Go.
Saying you know about my
Into
YouTube
my
channel.
speaker.
Yeah.
Does the
Just in case you ever get
LQ
lost,
group? Does
You're
the
gonna
H
have to be like, try to go search the words on this channel.
Somewhere else.
I don't think you have that.
Good.
I think we're just ignoring it because it's not.
Wow.
No, it doesn't.
Maybe we're both right.
I just thought of it.
Yeah,
like,
but no,
I said,
it needs to be a carboxylic acid.
Yes.
It makes you feel better. You're absolutely right.
I said the same thing, but with one down and with
So it's like 1, 2, 3,
down.
4.
Did you get the same notes?
Correct.
Absolutely.
Whatever your estimate
Okay,
is.
sure. The first one I think would be
Yeah,
wrong.
so that's the second one. That's a awkward place for a paycheck.
I've done that.
Yes. There's just a little awkward instruction. Yeah.
Oh,
And
you
here
know why?
actually we're missing a double bond.
It's
CO2
like this
is
because it's the
Do you think,
uh,
you guys think
CO double and CO
should be illegal for
because
18
there's
or
like
older?
that methyl group on there.
but you've got all the right carbons in your
I think
decarboxylated
that's a
product.
very nuanced subject that has a lot more to it than people think when
Good.
they first hear the term plastic surgery. And so I don't want
Good.
to make decisions
Yep.
for the people.
Well, I was what you think.
Good. Great work.
Laws are decided because everyone's having surgery.
And I think it's not my business.
What's
Well,
one
what?
thing you're missing, Rob?
Are speed limits?
Are you doing the top one or
Very
doing?
much so because they affect me.
Wow.
Oh, but you don't.
Okay, well,
You didn't
the
copy down the
carpool
grade
lane, what should be the
structure. There's a
punishment
method
for people clogging, sorry, not the carpool lane, the passing lane?
Yeah.
Do
And you
there
have
should be
it in the
punishment
purple
for
one.
clogging the
You
passing
missed
lane?
the methyl and the.
Um,
There you go. Does that help clarify where those groups are coming
no,
from?
I was like, what? That's not what it's drawing.
Like
Yeah,
if-
let me-
Okay, so there's always a truck on
We
Newton's
won't
Road,
make a
on the
carboxylic
lane
acid.
one away from the passing lane,
We'll make a ketone.
or like rows of
So
trucks.
four
Then there's
is
exit lanes,
cleaved
you're not going to
as
them, so you get to choose,
CO2,
do I go to the left
means
of
I'll
the
have
truck
one,
or to
two,
the
Oh,
right?
yeah,
of the
I
truck?
didn't have it,
Do I
yeah.
wanna follow
Three
the
would
natural
also be
gradient of the
connected
road
to
which says
Okay, that's
stay inward, yeah.
Yep. All right. Mapping carbons. I'm going to just count from left to right and say that 4 is the carbon that gets cleaved, which means I've got 1, 2, 3, and 3 is connected to 4. The hydrogen that is on the carboxylic acid after the hydrolysis adds to that alpha position. 3 is a CH group. Now it's a CH2 group. This isn't typically how you would draw the structure. It is a conformation of the structure,
So much better.
but you would see it drawn more like this. Takes a lot of energy to rotate around the bonds. In the bottom one, we do the same thing. 1, 2, 3, 4. 4 is the carbon that's cleaved. If you notice, 3 was connected to a methyl group here, so I just drew butanone. 3 is still connected to a methyl group here, so I could once again just Start by drawing butanone. Positions 1, 2, and 3. 3 is connected to a methyl, but now 3 is also connected to a benzyl. Do you remember last time when we were doing these alkylations, we actually numbered these positions as 4 and 4 prime, and we're free to do that again. Let me do it in a different color so it stands out a little bit more. Position 1, 2, 3. 3 connects to 4 and to 4 prime. 4 prime to 5 prime. That's just a confirmation. I could have also drawn this product like this. Positions 1, 2, and 3. 3 connects to 4, and 3 connects to 4 prime to 5 prime. Those are the same molecule. One other way that I saw somebody draw this product, which is correct, is to have the methyl group come down like this, and then the benzyl group come down like this. All they did was take that starting material, decarboxylate, copy, paste. It's not exactly pretty, but it's not at all incorrect. It's completely correct.
When you put it all together like that, do you list the CO2 and the ethyl group that pops off? As
No, we would.
those, or just totally other ones?
So we'll consider the ethanol byproduct. This step produces an ethanol byproduct because of the hydrolysis. And we'll consider the CO2 byproduct. So we don't need to show the CO2, we don't need to show the ethanol. A question I might ask on a test is something like, consider the reaction shown, what byproduct is not formed? If we were looking at this reaction, we form a byproduct of ethanol. Ethoxide takes away a hydrogen and becomes ethanol. We form a byproduct of sodium iodide. Sodium here finally leaves with a counter ion iodide after the substitution. We form another equivalence of ethanol. We form an equivalence of sodium chloride. And then after we do hydrolysis and decarboxylation, we also form an equivalence of ethanol again and an equivalence of CO2. So being able to look at the reagents and say, these are where the reagents are leaving is important. But predominantly we're focused on the major product. We're showing the major product.
It's from the water? The OH is from the water?
No OH. Not sure.
From the ethanol?
What OH? This OH?
No, ethanol is a byproduct?
Ethanol is a byproduct.
So it takes an OH from...
What do you mean? Takes an OH from?
Where's that?
Ethyl comes with its own O in ethoxide.
On decarboxylation.
In this hydrolysis step,
Yeah.
the oxygen on the ethyl ester stays with the ethyl group. Look back at the mechanism, we actually proved that. We tracked all of the oxygens during the mechanism and we said this oxygen stays with the ethyl group.
Is it two equivalences?
It takes a hydrogen from the acid. So that would be going back to Unit 4 and looking at the hydrolysis mechanism to make more sense of where those oxygens come from and go.
So why don't you just run it with water instead of acid? Wouldn't it?
Water is not a strong enough nucleophile. Water can react with ketones to give like a, well, no, water is not even a good enough nucleophile. Water can react with acid chlorides and acid anhydrides. Those are reactive carbonyls to react with just water. But the ester is stable enough. An ester won't react with water readily. It needs the acid catalyst to protonate the carbonyl and make it more electrophilic.
And it stays acidic.
What stays acidic?
The product.
After hydrolysis. Yes.
Can we use an H plus instead of H3?
Yes. Yeah, you could say H2O and H plus. Absolutely. H plus is generic, so H plus is almost never wrong. Yep. I want to show you guys the mechanism for decarboxylation because it is one of my favorite mechanisms. We already know the mechanism for hydrolysis of the ester. Protonate the carbonyl, attack with water, deprotonate that oxygen, protonate one of the other protonate the ester linkage group, eliminate by reforming a carbonyl, kick off the alcohol, and then deprotonate the carbonyl. Simple. Easy stuff. Old news. Decarboxylation just requires heat, which means the molecule reacts with itself. In order for this intramolecular reaction to occur, the molecule must get into a very specific conformation. It must rotate so that the hydrogen of the carboxylic acid is pointed at the carbonyl of the other acyl group. That means that the CO double bond of the carboxylic acid is pointed away from that group. So we typically draw it in this conformation, in plane. We're rotating around a sigma bond, and we're specifically highlighting the OH bond now. Can you see it? How can I make CO2? CO2 needs to have two CO double bonds. I've already got one of them. I need to get the second one. Do you remember how bonds form? Bonds break towards the more negative atom. Bonds form from the more negative atom. Bonds are always moving at the control of the more negative atom. That means that the CO double bond that needs to form, it has to come from the oxygen. Oxygen also has to get rid of its hydrogen. So oxygen will use the OH electrons to form the CO double bond. Now oxygen is free of that hydrogen, and it's formed the second CO double bond for CO2. But we have two problems. The carbonyl carbon is still attached to the carbon chain, and that carbon is now breaking its octet. So I need to break the carbon-carbon bond. Which way should I break it? There's no way to say it goes to the more negative or the more positive. It's carbon to carbon. So should this bond go to the carbon of the carbonyl so that we cleave that carbon-carbon bond?
It shouldn't.
That wouldn't help with the fact that carbon is breaking its octet. That means there's only one way that the bond can break. It needs to break to this carbon.
Wouldn't the two oxygens pull it towards it? Versus
These
the one?
electrons, those oxygens already have an octet as well, so they don't need any more electrons. Okay, this alpha carbon takes the CC bond then. But it doesn't want anything to do with it, so it shares it. Instead of it being pulled by these oxygens, that bond actually gets pulled by this oxygen, and the CC bond forms a carbon-carbon double bond, breaking the octet of this other carbonyl carbon, which means that the CO double bond also has to break. That breaks towards oxygen. What is oxygen going to do with them? It's going to claim the hydrogen. It's beautiful.
In one step? The oxygen? Wouldn't it go? It wouldn't go negative.
It's just a little rotation. It actually resembles the 3 arrows that you would show in the benzene ring resonance forms. From one resonance form of benzene to the other resonance form of benzene, you draw these like same 3 arrows. Do you recognize that this does not form our product? Well said. So Cooper, what functional group do we make? An enol. And the enol tautomerizes because we are in acidic conditions. We know that we're in acidic conditions because we just ran hydrolysis. Even if you're not convinced that hydrolysis means we're in acidic conditions, we have a carboxylic acid, so we must be in acidic conditions. In acidic conditions, I'm not sure I've given you guys this mechanism yet, so I want you to see this. Carbon is a good base. So carbon acts as a base and deprotonates the acid, which means the oxygen will share a lone pair and stabilize that carbonyl carbon. Tautomerization. That's our tautomerization process. Alkene acts as a base, and the carbonyl forms. And then, because this is acid-catalyzed tautomerization, we just see that simple deprotonation, and we're left with our carbonyl. So now you know what happens in the oven. It's beautiful. 6-membered ring, intramolecular reaction. Do you remember the requirement I said that must be met in order for decarboxylation to occur? Beta-acyl carboxylic acid. Can you see now why the beta position is what's necessary? If your carbonyl was at an alpha position, if your carbonyl was here, then there's no alignment for the oxygen to take the hydrogen. If your carbonyl is at a gamma position, if it's too far away, then again, there's no good alignment for the oxygen to take the hydrogen. Beta, I say beta keto most of the time because that's often what it is, but it doesn't have to be. The beta acyl carboxylic acid has that preferred 6-member alignment. All right, here's something that I would like you guys to solve for me. Oh, sorry, hang on. Don't copy that yet. I encourage you to work in groups on this. This would be a great problem to do in groups. But if you want to take a stab at it on your own, then I encourage you to try and convince somebody else of your thought process and prove to them that what you solved makes sense.
Is that the only product?
There's a byproduct here of methanol and carbon dioxide, if that helps you. although I might not, I probably wouldn't give that to you on a synthesis. I wouldn't tell you that those are the byproducts. I'd expect you to recognize the reagents and their role in these steps. You get to decide the starting material. There's only one right answer, though.
So this is what decarboxylation. Just a methyl group. Oh,
That's okay. I didn't see the heat. I wanted to make sure you have it. There's so much thinking happening in here. I can hear it. All right. I think you guys have shoved that boulder enough on your own. It's time to work with someone else. Start collaborating. What insights can you glean about this reaction that you might be able to work it backwards?
I don't know which one,
Oh, you
which
saw it?
carboxylic acid goes to which.
Yeah.
That is the question.
So
disappears.
So work with them, and you are turning some business here, which is good.
Wait,
This is the solidifying process. These guys are learning the same time. You're learning learning is usually that second time that
it
you
turns
learn
into
yours is going to be a lot better.
into
So
Um,
be comfortable and use your
what do I
resources.
do?
Yeah. So don't be afraid to look things up.
One, two. Oh, propene. Propene.
Your computer wasn't
S
suited for this one?
comes the carboxylic acid and forms. So I'm
What do you know that
guessing
each of these steps do? How can that tell you what to put back in or tear out?
Just one equivalent.
One equivalent.
It's only one?
Sorry, I don't know what you mean. One equivalent.
Oh. Is it that or this is an H?
Why don't you collaborate?
Oh.
See if you've got a thought process that they think they can help you with.
I'm just curious if that.
This is really beautiful. The curvature of it. I think maybe I should do that with like my rigid lines. My lines are like.
What have you said?
Could be too. So like
So
puzzle the first is
that
always trying
last
to
step
figure
makes
out
you think
where
of what?
But then I'm like looking at the fact that he has 2 steps, though. It's like
So it's required to be a ketone to do. What step do you think is happening there? What reaction is happening in that last step?
I think there could be a problem.
What is the name?
Yeah.
Is that what you're thinking, Russell, too?
I
You think this last step is a decarboxylation. So we have removed what?
Maybe there is another.
We removed CO2, which was present in the molecule as. You're on the right track. Okay. So the requirement for decarboxylation is it? It has to be a beta ketone carboxylic acid, so like less of the ketone.
But wouldn't you need 2 equivalents of the NaO?
So that gives us options. That means it could be aldehyde, ethyl chloride, a anhydride, an ester, an amide, right? All of those would technically count for us.
Yes.
So
you're right.
given the functional
Yeah.
group you see at the end, what makes more sense to be the acyl group in step 4? That's your question. You're used to thinking of it as a ketone because of the problems we did. But now diversify your acyl groups. What other option could it be?
I just had to take the choice out of it, and I was like, he said these were good. So I'm gonna start with these.
I like that. I like that. I was just, well, I tried to do that.
No.
But then I was like, how am I supposed to keep that?
Makes sense to me.
So you don't think that last step is
You don't want to take this.
oh wait, no, that's what
Yeah.
the.
Just like,
Maybe
they have
methyl
most of it
malonic
done
acid.
already.
Okay.
No,
I
I
totally
really
forgot.
Sometimes I'm like too practical.
Let me ask you this.
How are you gonna get that? It's like, it doesn't matter.
How would this change? Is there a way I can change the colors to use it? How would this mechanism change if instead of an R group here, this was an OH group? Now instead of a CH3, it's an OH. Now instead of CH3, it's an OH. Now instead of CH3. Remember we said that this has to be an acyl group, beta to the carboxylic acid, but we didn't limit what that acyl group could be. We just said it has to be a CO double bond, which means taking it from a ketone to an acid means that I'm left not with a ketone, but with an acid. And I did that in a different order so you could erase it and you're like,
So much
copy paste if you
happens
wanted
to.
to.
Yeah, I've had to do the homework with
Carboxylic acid in that first step with NaOMe, it's just going to do acid-base chemistry. So why start with the carboxylic acid when you can make it a carboxylic acid with H3O+.
When you did this, did you work backwards?
No, I actually
Like you're saying, this is not an acid. So how is that going to be decarboxylated? Yeah, yeah. Yeah, at the very beginning, if you have an acid and an ester,
What up?
and then you do.
The far side, the ester would be the methyl.
My question is,
Why is it not
you're
both?
seeing this group
Yeah.
Because the mechanism can
From the
only be
beginning.
one.
Didn't copy it exactly.
becoming
I think that
That's true.
right? How does
Because
an ester
one of them is just an R group.
Yeah. Yeah.
In this case, it can be either.
But that's not quite
This to get on there
But the
somehow.
mechanism
That's
says
a
it can only be one.
This is a beta ester acid.
like,
So maybe
Right.
do copy that down.
Right, like,
you can see where
I'm gonna make alkene. He's like, you just put it in here, bro. Think you can do anything about that. Not my problem.
Oh, did you learn from Ron? Did you write it that way? Or did you? Oh, did you learn it? Oh.
Oh yeah, you put it over here.
There's some discrepancy about what you've written in the carbon chain, but it's
No, just
definitely
now.
on the right track.
Today.
Oh, at the beginning.
And
okay, I'm like,
yeah, and that is,
No.
so if you fix that carbon chain, if you write, you've got one too many hydrogens.
Yeah,
That's right.
Next week, and then we have like the reviews.
Do you agree?
Yeah.
You see how it leaves you with the functional group you have at the end?
Yeah, that real hard.
Yeah.
We need 3, 4, 5
There you go.
I just confuse myself drawing lines.
That's
I see what
You
you're
have
saying
it. You
now.
have it here, but you.
Yep.
I know. It's just like not. It's nice not to have to worry about anything else.
Well, she starts with 2.
It's like, this is complicated.
Oh, so that's the modification.
Oh, nice.
No, I'm
But
signed up
You
for
had
it,
it away to the away.
but I'm still waitlisted online.
Well, actually,
Oh,
it-
okay.
So I got
Well,
yeah.
because having the carboxylic acid here actually messes with the
I can
sodium.
actually see
Like,
how.
How you just get half of
no,
it.
This one.
So having an ester
Yeah,
is
so it's like hanging out on the side.
It gets rid of all the
Because
esters.
if you look at the.
I think it's
bones,
easy.
it's like one
Yeah. You taste it.
clear taste. So it gets into that position.
Good work.
Okay.
And then once that's broken off, there's no other
No,
position.
I'm not. One, you've got one too many positions here and here compared to here. You've got too many carbons. That's an easy fix. The other problem is this ester will become an acid and decarboxylate, which would leave you with a ketone, not an acid.
Why did I do the other? Where's my paper?
So, how could this acyl group change such that you are left with an acid at the end and not a ketone? Not a bad idea. The problem is having an acid here at the beginning means that this step just runs acid-base chemistry at the carboxylic acid, not at the alpha position. Is there any other way that you could change this at the beginning and then make it an acid at another step? You're making this an acid at another step so that you can decarboxylate it. Could you make this an acid at a different step? What starting material would it need to be then? How do you guys feel?
I think we got it.
Did he get you guys there? Did you
Yeah.
you kind of met halfway?
I used there.
Nice. Way to go, guys. Good teamwork. You guys feel like
Did we get it?
I don't know.
I don't know if you looked at it.
Hey Josh, please.
first of all, there are more carbons here than there are here.
Thanks, Nintendo.
Do you agree? Yes. Alpha carbon, active carbon. Yeah. Well, how are you going to get this to be a carboxylic acid? Hey, you do the same thing here. Isn't that what you said? I thought you were picking the thing on the left. You were picking the thing on the right. Oh, I thought we were looking at this.
That makes so.
Now see if you can
That makes more.
catch camera on this video. Yeah, yeah, you did. That's exactly right.
Okay.
You guys
Is it called methylmalonic acid? Dimethylmalonic
working on this
acid?
still. This step is good. The reagent you
I
need.
think malonic.
All right, should we go through it together?
Common name, malonic
And we'll take a break.
acid.
Ooh, it's time for a break. Oh, it's 6:07.
No, I'm wondering about the name for malonic acid. Sorry.
Why is it called that?
Methyl? Like, would it be methylmalonic?
Methylmalonic ester. No, it'd be dimethylmalonate. You remember esters get O8 at the end? Common names usually don't have the O though. So this malonic acid is when these are two carboxylic acids. Malonic ester is kind of a misnomer because it says malonic, which is not the name for an acid. That's the name for an, sorry. Malonic is the name for an acid, not the name for an ester. So it'd be malonate. This would be dimethylmalonate. Here's the main trip up that you all ran into. I know how to get a ketone functional group at the end, but I don't know how to get a carboxylic acid functional group at the end. So let me say this. If instead of having a CH3 at this position, I had an OH, what changes? The carbonyl still serves its job during the decarboxylation. It could have also been an ester. Although in acidic conditions, in order to make this an acid, an ester here wouldn't have stayed an ester. It would have also become a carboxylic acid. It could be an amide. It could be an acid chloride. It could be an acid anhydride. It could be an aldehyde. It just needs to be an acyl group. So why couldn't that acyl group also be a carboxylic acid? That would mean here, I have not a CH3 but an OH. That would mean here, I have not a CH3 but an OH. That would mean here, I end up with a CH3 and not an OH. We said that it needs to be a beta acyl group, and that acyl group could be anything. So that helped a number of you say, I'm all right having two acyl groups at my starting material, and one of them will be an ester, and one of them will be an acid. So this is where I saw a lot of you go from there. And what I imagine you were saying is, this ester is the reason that we need to use sodium methoxide. It needs to be a methyl ester. And this is the alpha position that we'll do alpha-alkylation at. And then this ester will be hydrolyzed and decarboxylated, leaving me with the carboxylic acid. On the right track. The problem is, carboxylic acid is orders of magnitude more acidic than an alpha position. So when you take this acid ester compound, a beta ester acid, and you react it with a base like sodium methoxide, you don't create a nucleophile at the alpha position. You just deprotonate the acid. So this doesn't allow for any chemistry to occur. But I don't need it to be a carboxylic acid here. I need it to be a carboxylic acid here, which means I can make it a carboxylic acid during the hydrolysis. Ketones will not hydrolyze to be acids. But esters will, and you already knew that because you were all saying this ester will hydrolyze to a carboxylic acid and then be decarboxylated. So let's make this an ester. What's a good carbon group to put on that ester? The same carbon group. And so I was not trying to trick you at all, but the other compound that is good at alpha-alkylation is a great starting material for this synthesis. Dimethylmalonate reacts with sodium methoxide and some group to give me this. That means that I've here also got that dimethylmalonate plus a new R group. And after the hydrolysis, I get that alpha-alkylated malonic acid. That's a beta-acyl carboxylic acid. And it will not leave you with a ketone like we saw before with acetoacetate. It will leave you, when I cleave off one of the carboxylic acids, I get another carboxylic acid. Great. So now the question is, what is the R group? During the alkylation step, the alpha carbon acts as what? During alkylation, alpha carbon is the nucleophile. So here's alpha. I know earlier I taught you different ways to number those. You still have all those ways. Where is alpha in the product? Same spot. It's still alpha to the one remaining carbonyl, which means beta was what carbon in the alkylation? Not the nucleophile, but beta was the electrophile. So earlier when I was telling you count 1, 2, 3, 3 attacks 4, here we're just saying alpha attacks beta. So I need to have beta attacked. Beta is connected to this 2 carbon group, and beta needs to have a leaving group. Here's a common mistake that I got from a few people was adding this reagent. No, sorry, just kidding. Really bad. I'm not trying to shame you. This is a very common mistake, and I get it. But there's a couple of problems here. This can't do SN2. sp2 carbons they require way too much energy to do sp2. So we can't use an sp2 carbon to do this substitution. The other problem is it's not enough carbons. So it's got 2 issues. And then one other issue that I saw here was having a structure like this. What's the problem there? Just too many carbons. This would be beta and then a few other positions, but I want to have beta and then the alkene. So beta connects to the alkene and beta has a leaving group. Just like earlier we said position 4 needs to have some leaving group when we do our substitution. This is a bad, like this 4' had a leaving group, this 4 had a leaving group. So when we draw this in, alpha attacks beta, and beta is connected to the 2 carbons of the alkene. I'm going to map it again so I make sure I don't lose anything. Alpha attacks beta, and beta is connected to the alkene. That was a really good exercise. I really enjoyed the way that you guys pushed into it, right? Trying to figure out what possible combinations can I have in the starting materials that leave me with this carboxylic acid at the end. And there was just one possibility. You had to have 2 esters before hydrolysis so that when one carboxylic acid gets decarboxylated, I'm left with the other carboxylic acid. As opposed to having a ketone and a carboxylic acid, then when the carboxylic acid is gone, the ketone is left. Or an aldehyde and a carboxylic acid, which will only leave the aldehyde. All right, any questions on that synthesis? Good work. Why don't you take a 5-minute break? And I will consider what we're going to do next. Oh, I have a multi-step synthesis. I think that's what we'll do for the rest of the class, to be honest. So if you want to head out early, I don't know. Maybe I wouldn't encourage it because it's still a good time to practice these reactions. But I'm not going to move into the next section. I'm not going to move into the alpha condensation reactions until next week. So we'll do a few more multi-step synthesis with what's left in our time.
Can I just? I'm pretty sure for the multi-step.
He's been asking me about every student, and I tell him I can't say what
Yeah,
people got on
Hopefully you
their
can read
exam.
all that.
Oh, yeah.
He actually has asked everybody in this room.
I think you could have crossed it.
Thanks for coming yesterday, bud.
Yeah, it was good. Thank you. I didn't like your exercise. It made me embarrassed.
Well, it made a lot of people embarrassed because nobody did it.
Like, I hate that shit so much.
Yeah. I mean, I thought it was fun.
It's better to have it.
Yeah, I agree.
It's kind of fun.
It would have, otherwise I was just talking at people, but that was like a silly little way to connect with chemistry. Yeah.
I saw people do it.
I saw a video recently that was like, in high school, that's never going to fly in college. And then a video of a college chemistry class, and they were actually all doing the same thing, and I was like, I want to do that.
Is that what gave you the idea?
Yep.
Oh, that's smart.
Yep.
That's funny.
But I connected it differently. I was trying to show the transmission of energy, right? I was trying to say, like, why does the entire atmosphere get warm?
There's more people.
Well,
that was also the part people were most comfortable
Yes.
with.
One, I needed a willing audience, and not everyone was willing. Two, not everyone understood how to show their energy. Some people would just like start going and then stop. And I think I needed to better explain, like, everybody's moving a little bit, okay? I needed to get everybody moving at first, and then I wanted to see more people excited, and then moving to lower energy by making other people higher energy. It would have worked really well with a willing audience and a packed audience, and better explanations.
If it was fuller, everybody would.
I think what I probably should have had people do is like show little energy. Okay, here's little energy. Show medium energy. Okay, here's medium energy. And now show excited absorption, right? And then had everyone start at low energy, a few people move to high energy, and then transmit everybody to medium energy. Didn't get there though. That's okay. At least that wasn't in the recording, because that would have been more stats.
Oh, the audience.
Yeah.
I'm surprised you thought people would do it. I'm like, you need to know your
I
audience.
did, and a few people really got into it.
You know,
They loved it.
I was not surprised.
Yeah, that was a good time.
Alright, you know this video. Can you head out?
Have you signed up at the tutoring center to teach OCHEM yet? To tutor OCHEM?
Dude, I don't even know if I'm gonna do it next semester. I'm starting my units next year.
Yeah, I get it. I get it.
I don't.
You'll never understand it better than when you're tutoring.
I should. I really should.
And you already understand it well.
Yeah, I'm gonna have to purpose it.
Yeah.
Because I'm gonna forget everything.
Yes, you
Well,
will.
I'm already gonna be helping Sebastian next semester.
Good. Good.
Because he's already asked me.
OCHEM too.
And I'm like, prep as much as YouTube.
That's why I put him
So
there.
he's gonna start doing that.
I mean, I believe education should be free, so that's why I actually feel a little bit guilty that this is my job, that you guys have to pay for it and I get paid from it, because this is knowledge and I'm not trying to gatekeep it. So I figure if somebody can't get their foot in the door to take a class because it's too expensive,
Yeah.
they should be able to learn it for free.
Well, you're paying. Yeah, probably. Don't put a paywall behind it.
Exactly.
People are paying for
I don't think people should have to pay for education. Maybe pay
You don't have to.
pay to be certified,
You're paying to be certified.
but pay to be
Well,
educated.
yeah, I think you should go and take any program when you're getting accredited.
Okay, I
You know
see.
what I mean?
Yeah.
Even that's kind of. All right.
Enjoy your break.
See you on Tuesday.
See you then. Oh.
Oh, okay, bye.
Oh. You had a question?
Yes. I don't believe you explained why I was wrong,
Because I said so.
and you gave me credit for me. I circled.
You made it very unclear what answer
Yeah,
you wanted,
yeah, but you
so
gave me-
I went with the more clear answer.
Yeah, you gave me. Yeah, I didn't choose that one though.
But you circled it.
Yes, yeah.
So
I should have erased. I didn't notice that I circled it.
You're right. Honestly, I was like, it actually seemed like you went back and added that. And I know you sent it to me not long after you submitted the test, but I looked at it and I was
Oh,
like,
I see.
it looks like you went back and annotated your notes. And I was like, this is the one he circled. That's the correct answer. You would have gotten partial points because you chose a reduction mechanism anyways.
Yeah.
But you
But can I?
made it unclear. And on my tests, you know, on the front page, that big paragraph that no one rates on my exams, I say,
What?
If your answer is unclear, you may lose points. Well, your answer was unclear, and it gave you points. So, falling forward, right? Failing upwards.
Where?
Task successfully failed.
One Oh. Okay. Can I lose that quarter point back?
No. I'm afraid not. Oops. All right, guys, here is your next multi-step synthesis. And much like the room, we are turning the heat up a level. I think that I combined different things there. We're turning up the heat. It is hot in here, right? Yeah. Get ready for some decarboxylation in here. I am not telling you how many steps you need for this multi-step synthesis. Just gotta figure it out. You are allowed to use what? You're allowed to use any number of carbons in reagents that you add. You're allowed to use inorganic reagents. I will tell you that you're keeping it to reactions in this unit. So far we've done radical halogenation, acid catalyzed halogenation, base catalyzed halogenation, chloroform, alpha-alkylation, and decarboxylation by means of hydrolysis and decarboxylation. So those are the only reactions that you'll need to use to solve this multi-step synthesis. But an untold number of steps, an unknown number of intermediates. Oh, you know what? I did lie. No, there's one step that you'll need to call back upon old chemistry. Sorry. Yeah, there is one step that you will need OChem 1 chemistry for.
DCC here?
Yes. You need DCC. This will actually just run acid-base reaction. Carboxylic acid with amine will just protonate the amine. It certainly won't attack. So DCC helps to chemically force this to happen.
Everyone else knows that there's supposed to be DCC here. It's in the normal notes.
It's in our notes. Yep. Though I've been thinking about changing those notes. I saw how those notes got copied down on the worksheets and in some people's handwriting. I don't know if it's for the best. You know what I mean?
I'm not a teacher.
But I mean the carboxylic acid derivatives flow chart, it's just too tight.
It's a lot of
That was
information.
I love that chart.
I like it too. But it's really tight and I feel like the information gets lost.
Yeah, I had to color code it.
Color coding is useful. They had this flyer for my talk and it said I was in the engineering department. And then at the start of the talk, I told the guy actually apologized. He's like, sorry about that mistake on the flyer. I'm like, oh, it's okay. I'll wear it as a badge of honor. And then at the start of the talk, he said, John Flood is an assistant professor in the biology department. Like that, I do not wear as a badge of honor. That is gross. And then he goes on to say he got his master's in chemistry and he teaches chemistry, and I was like, why would I be in the biology department? I think it's just a slip of the tongue, you know.
Applied chemistry.
No saying it's science, but oh. I want to review the tips I give on multi-step synthesis. Map your carbons, which is just one step longer than counting your carbons. It says, where are your carbons in the starting material? Where are those carbons in the product? Brainstorm, which means start thinking about what reactions could be useful here, and potentially write them down so you've got that note. And work forward and backwards. Maybe you're not sure how to move forward, maybe you're not sure how to move backwards, and you want to try and do both of those.
Oh, I thought I was in trouble. Okay,
Does
thank
look
you.
like
I
trouble.
was very scared. Okay, thank you.
Mm-hmm.
I was like, in front of everyone. You're firing me?
You're fired.
I didn't even know it worked here.
You have 5 minutes to pack your things.
I need more than that.
Oh, I'm sorry. Oh, sorry. I've made a terrible
Thank
mistake.
you. Thank you.
Oh, my
Thank
goodness.
you.
I was getting so curious.
Is that possible?
I was like, I'm going out of there.
Not easily. No, not.
Oh, made my year.
I thought you made
Wow.
a mistake, and I was like, oh, you copied it. Oh no, I made a mistake. Yeah,
That's stressful.
I apologize.
Okay, we'll forgive you.
Not intended.
It's fine.
Oh my god. No, I'm like, map your carbons, and everyone's like, none of them
I know.
end up in the final product. You just start over.
Oh wait, you got rid of.
Here's the one step. Throw this away and get a new one. So with that in mind, do you Oh yeah. I will be honest. This is from a different class. This was the professor was Pyotr Respecki. I don't usually organize them quite like this, but he basically went through the textbook and just wrote out notes for the textbook. But yeah, you're in the right region here.
Yeah.
No,
It's not, oh no.
it's not basically.
Big to different.
I mean, there might be steps that feel similar, but
It's the same
oh,
thing.
well, here's a problem. We can't do SN2 on an sp2 carbon.
Oh, you're right, okay.
Yeah.
Oh
That's actually an Ochem 1 principle, but that's not the Ochem 1. Oh, I see what you're saying. Hold on to that. See if you can convince them of that.
Nah. You hydrogenated?
How to do elimination. Well, lean on them. Maybe they can inspire you.
Yeah, okay.
Wait, so you do like a nitrile, and then you swap it with a phenol, and then you reduce? Ah, you can't do that.
So here's a question. We saw this reagent
Yeah, you
with
could do
this
that.
reaction as well, or like with alpha carbons. So one question I might have is, do you think it would happen at one over the other, or would it even matter?
No, because there's no hydrogen to steal from here. So if the bromine here, it's going to eliminate the same way.
And then what about base? Is there maybe a way we could change the base to make sure that we don't do any sort of like substitution type reactions? You know, hydroxide also likes to be a nucleophile, not just a base.
Oh, you can make it big and bulky? Like a,
So to make sure that it's only doing its job as base.
like a butoxide?
Wonderful. Way to go.
For some reason, my mind always blanks and it's like, what's a base? I'm like, OH minus.
That's a good answer. That's like the base. We tell you that on the first day of gym. You have a thought?
I think we want to do,
It's, well, you're adding this. Okay, so I think what you're suggesting is the alpha condensation, right? I haven't shown them that yet. Yeah. Yeah. And
There's 3 steps.
and that would work. I think what we want after we add this is extra heat and base to drive the condensation. Because it starts with aldol addition, which will give us an OH group, and then we need to drive it further to do condensation. That would give you the
I don't need to
alpha
worry.
beta condensation. Yep.
I've only seen it like.
Correct. Yeah. We haven't. I don't actually usually show you that. I guess that is probably a wrap. I don't know why they don't do that as a wrap. You have a lot of ideas. How would you go from here then? Oh, it wouldn't leave you with this. Not the OH. This would become OH acid decarboxylate. And you'd be left with yeah. Yeah, exactly. But you decarboxylated ketone. You need to decarboxylate carboxylic acid. No, you wanna leave with the ketone.
Oh, I see. Okay.
You ended with carboxylic acid.
No, yeah, I was still thinking about
Oh. I see. So yes, the way you had it, methyl here, you do it methyl.
Pretty much.
Sorry about the
It's
noise.
like, you could add here or here, because that you can also add the alpha position, but it doesn't matter.
You know what?
Right, because
You're not
as soon
off
as you
to a bad
eliminate,
start.
like,
This
you
is
can't go this way, so
this is a
you can't go that
possible
way,
route.
so it can only eliminate
Here,
that way. Right.
you're trying to add this position 3 to 4,
Mhm.
but we actually don't want acidic conditions. We want basic conditions again to turn 3 into a negative charge nucleophile so that it attacks 4, which would do alpha alkylation, which is actually something that we said works best up here with this reagent. So maybe we flip it and we say, let's add this alpha alkyl group first,
Okay. Where would it, now that I got
just the
my
way
name,
we've been using it.
finally,
Into the 3 position.
That's right, because that's the most acidic condition, so that will be deprotonated to make the nucleophile. So it'll look very much like this first step. Deprotonate as group 1, and then get an alpha alkylated.
Do you know how to alkenify that alkane?
Okay, good start.
Oh, that's cool. Oh, okay, yeah.
This is your open one from my class. Wow. I don't remember this reaction. That's good.
Yeah.
So this is a possible route, but we now lose all these carbons, and actually we can still get them back by a similar process of alpha alkylation. But if you're going to do alpha alkylation anyway, it makes more sense to do it first. Like we said earlier, alpha alkylation works best here than it does here. So if you're going to do this and then alpha alkylation, just flip the order.
And like rotate through all the rural hospitals down there.
It does seem weird, yeah. Do you think there's any way that you could add that to in later?
I wanted to do they only started taking applications in 2025. So
And think about the reaction from this semester, from this unit, where we didn't have
the
them.
MD from
Radical
that's green program.
CH3 PA.
I'm gonna apply a bunch of places.
That's true, yeah. So you're saying 3 attacks
It's
methyl
DO school
and methyl is
yeah.
metal.
I go to UNR,
But you
UNR,
lost
school
the
in Reno. Yeah, University of Reno. CU, or not, I guess it's not CU.
Purple. Now, that
Yeah,
carbon
Colorado, sorry.
doesn't have a good
Exact
backing group.
Those are all empty.
Yeah. Yeah.
Perfect. Now when the carbon
Yeah.
attacks, bromine gets kicked off.
Yeah. I'm excited about the Rocky Mountains too. Like, the Utah.
No, actually, your OH
Or
minus
like
is deprotonating.
I don't
Makes
know
sense.
what the Colorado one, they opened
Let's
one in
imagine that this is
Montana.
NA.
The one in Billings would be cool. It's like right up my folks
We
too,
ignore the
so-
NA
Yeah,
because
they live like just a couple hours away.
that means that the
So it'd be,
byproduct
my grandma
here.
was real.
Do you know how to, do you guys have ideas on how to
Pretty
Well, we have no
convenient.
problem.
They have like
how to
Now,
turn the
uh,
alkane
we'll
into
get
alkene?
after
federal
this
ones and stuff,
after,
which that
Yeah.
would be like
Alkene?
and it will
just the new
turn it
Montana
into a
carbon.
carbon.
So that'd be like a pretty big
So I don't want to use
consideration if I go there or not.
hydroxide.
Like, I don't
Yeah,
really
put light on
take
it and
out
reduce
private
it.
loans
Won't
like an
change.
And
LLC.
hope it forms the alkene.
We want it to match the estrogen.
Good.
Yeah, Florida just graduated.
Yeah.
Perfect.
How
There- yeah, I saw
Oh,
they
wait.
have accredited.
And
Do they have
oxides,
loans yet?
they do
Or is it still
exactly the
ongoing?
same thing,
you gotta do the
but
alkylation.
hydroxide can run a side reaction. Ethoxide
You could probably do
won't.
it in and over.
Perfect.
Maybe not the
Now
church.
show me what happens after your. Oh, but actually, this is
To get a
still.
halogen on there.
Oh, it's actually wow.
But it's like
Yes.
closer to the
Yeah, okay, okay.
Yeah.
Good.
And then.
Okay,
Now
if you're
I'm
applying
gonna send
47, it shouldn't be a problem at all.
Yeah.
You should be sort of.
Yes.
Carboxylate.
Yes.
I don't know, I think if there's one in it for.
Decarboxylate things.
perfect.
Yeah.
Oh, and then
And
you
actually,
reduce it.
there's
It can only go one way.
would the radical form at the alpha position ketone, or would it form at the alpha position? The radical would be stabilized
Fine.
on either one.
I guess you could do slightly.
It's true. And the other product would still give you the same thing. Good.
Yeah.
Okay.
There's one.
Exactly. I might use different reagents. I probably wouldn't go for an E1. I would go for an E2. And when going when
Like that's more like.
yeah, when going for E2, I'd go for the Galpy base, which loves elimination and doesn't. Yeah, yeah.
I feel like it's
Perfect.
like the last 2 years stress throughout that stuff, and I'm just like,
What do you guys think they
should apply, and what's gonna happen is gonna happen. Just be like, no,
Yeah. You know what, James? You've got a process that works there.
I'll
That's good.
take it.
Mm-hmm.
Can you show?
How about you?
Same thing. You kinda
We
like-
worked it out together.
Okay, good.
I kind of did it in a different order.
You did elimination last, decarboxylation first. The only thing I'd say about the elimination is I would use a big bulky base, something that loves to just do elimination,
So like,
whereas water does E1, which is sometimes E1, sometimes SN1. Terbutoxide is a great thing to use if all you want to do is eliminate.
okay.
Yep.
Cool.
Take that. I love that you have a process that works. Because the subtext is, that's weird, but it gets you there.
Yeah.
That's correct.
But
I'll
it's
take
not like,
Good enough for me.
or I should say, if you have like a number like
Yeah.
here or something, then
Actually,
you would run.
it'd be a mess over here.
So yeah, you're gonna be, then you might.
Correct.
Like,
You're exactly right.
So you see that, you see that preferential is this big base.
And that point, you'd have to go with the smaller base
children,
and just put up with the bypass.
It's like the typical neurotic.
All right, guys, we are wrapping up on time. Listen, in my Gen Chem class, I told them once that I wanted to show them an Instagram TikTok. So I don't care. Anyways, you guys came up with a lot of good routes for this. That says that there is not just one answer to get to this final product. Here is the route that I was envisioning. I want to use alpha-alkylation, decarboxylation, radical halogenation, and elimination. One thing you need to avoid, if your reaction process at any point tried to add this group so that your alpha carbon connected to an alkene, we're not allowed to do SN2 on those sp2 carbons. So this is never going to help us in an alpha alkylation product. Also, the same thing goes with our Friedel-Crafts alkylation. These sp2 carbons, they're just not reactive for these purposes. There are a number of different orders that you can do this process in, but if you're going to do alpha alkylation and decarboxylation, you notice I lose my ester, I lose entirely my carbonyl. Here's what I see when I map my carbons. I see my carbonyl position at 2, my alpha carbon bonding to a new beta carbon. That beta carbon is benzylic, it's connected to the ring. At some point I want to form an alpha-beta bond, so I want to do some sort of alpha-beta elimination. That means I need to have elimination in this process. If I'm going to add a bond from alpha to beta, then let's do alpha alkylation. First, I need to add a base. Does it matter what my base is? It does. If I add hydroxide here, it's game over. I don't have my ester anymore. I'd have to reform my ester. Hydroxide will hydrolyze my ester. So I need to add a base that matches my ester to make sure that it doesn't turn my ester into a carboxylate. Then I need to add position beta. Obviously alpha is not already sp2, so beta does not need to be sp2 here either. Beta needs to be a benzylic carbon connected to the pH, and beta needs to have a leaving group. So chlorine, iodine, bromine, tosylate, OTS, all of those are good answers. Those are the only carbons that I want to add during this process. I just wanted to add that alpha-beta position, and beta is connected to this. Now, earlier I said I want to do elimination. To do elimination to form the alkene, I will need another good leaving group. I have no good leaving group here. So I could do radical halogenation right now, or I could do radical halogenation later, and I could do decarboxylation right now. So I'm going to show you guys two different routes. If we do radical halogenation right now, there is definitely a preferred position, and that is the alpha carbon between the two carbonyls. That alpha position would have a radical intermediate in resonance with two oxygen groups. Oxygen being more electronegative would like to take that radical, as opposed to radical halogenation at the benzylic position, where it's only carbons holding the radicals. However, I could have also run my decarboxylation right now, and that would leave me with alpha connected to beta and beta connected to my phenyl group. Here, I could run I could run halogenation, and this might be debatable. Would the radical halogenation prefer a radical at the alpha position, radical in resonance with a carbonyl, or would the radical prefer to be at the benzylic position, radical in resonance with benzene? Let's draw them both, because it actually doesn't matter which one forms. It would still give us the same product after the end of our synthesis. Back down in this original green route, after I do radical halogenation, this is where I want to do decarboxylation. And I didn't decarboxylate it. Never say never. So now you can see I actually have the same structure twice. This route gave me this structure, and this route gave me this structure. So whichever route you took, you're ending up at this place where you're ready for elimination. And you can take that elimination a lot of different ways. I would prefer a big, bulky base, something that's only going to do elimination, something like tert butoxide. You could run this with hydroxide and heat. You could run this with water and heat. You just might risk doing elimination and substitution. And then there was another route, which was from this alpha halogenated product, you could run that elimination and you could create the alkene before running decarboxylation.
sometimes it's nice to be able to have a lot of different routes because it gives you a safety net. And sometimes it's scary because it means if I follow this rabbit hole and it's a dead end, how far do I need to backtrack before I find a route that's actually going to be useful? And don't forget, this is both creative thinking and critical thinking. You are looking at all of the possible reactions that you have at your disposal and then trying to say what is plausible and what is not plausible. So be creative about what you can use and then be critical about what actually is allowed and what is not allowed. Two sides of the same coin, but that's a skill that you have to develop. All right, thank you guys for your time. Have a great Thanksgiving break, and I will see you next week, Tuesday. No class Thursday. That'd be crazy. All right? Take care.